Dear learners, welcome to Anjak Virtual Classroom. I am Dr. S. Saravanan, Associate Professor, Department of Chemistry, Ayyanararaja Neumann College, Sivagasi. In this course, you are going to learn about conformational isomerism. And we are going to discuss about the conformation of acyclic compounds. Secondly, the Bayer-Strain theory. Then the conformation of alicyclic and bicyclic compounds. After discussing the conformation, we are going to discuss about the factors that influence the stability of various conformers. And then finally, the influence of conformational isomers on the chemical properties of molecules. Before going to discuss about the conformational isomerism, let us go through some of the basic terminologies. First of all, what are isomers? Isomers are the compounds having same molecular formula but different physical and chemical properties. And these isomers can be classified into two types, namely the structural isomers and the stereoisomers. The main difference between the structural and stereoisomers are: structural isomers have same molecular formula but different structural formula, whereas the stereoisomers have same molecular formula as well as the structural formula, but they have different three-dimensional arrangement of atoms and groups. The various types of structural isomers are the chain isomers, the functional group isomers, the positional isomers, etc. The stereoisomers are further classified into two types, namely the configurational isomers and the conformational isomers. In this course, we are going to discuss about the conformational isomers. What are conformational isomers? Conformational isomers are the stereoisomers which arises due to the rotation about a single bond. The conformational isomers are also known as the conformers or rotamers. The energy required for the rotation about a single bond is very low, and therefore the conformers cannot be separated at room temperature. However, at low temperature, the rotation around the single bond is restricted. Under such circumstances, the conformers can be separated or detected by physical methods. Moreover, the relative population of the various conformers influence the physical and chemical properties of a molecule. Then, the condition for the molecule to exhibit conformational isomers. For a molecule to exhibit conformational isomers, it should obey the following condition. Firstly, the molecule must have single bond connecting two atoms, and the connected atoms, that is, both the atoms connected by a single bond, must have at least one substituent. If these two conditions are met by a molecule, then that molecule will exhibit conformational isomers. And what about the number of conformational isomers? For any molecule, the total number of conformational isomer possible is infinite. That is, infinite number of conformational isomers are possible for a single molecule. For example, molecules like methane, water do not have conformational isomers because in these molecules the two atoms are connected by a single bond, but the hydrogen atom does not contain a substituent. In the case of hydrogen peroxide, consider the single bond connecting the oxygen atoms. Here, each oxygen atom is connected to the substituent. Therefore, conformational isomers are possible for hydrogen peroxide. In order to better understand the conformational isomers of organic molecules, it is necessary to know the various projection formulae of three-dimensional molecules. They are wedge and dash formula, Neumann projection formula, Scalars formula, and Fischer projection formula. Apart from this, we also need to know what is dihedral angle. The wedge and dash formula shows the three-dimensional molecule using thick wedges and dashed wedges. The thick wedge represent the bond projecting towards the observer, whereas the dashed wedge represent the bonds projecting away from the observer. Here, the lines show the bonds which are present in the plane of the page. The next formula is Neumann projection formula. It is the best projection formula to visualize the conformational isomers. To draw the Neumann projection formula, the molecule is viewed along the carbon-carbon single bond. In Neumann projection formula, the front carbon is known as proximal carbon. It is represented by the dot, and the three atoms or groups attached to this carbon are represented by the lines radiating from it. The back carbon is known as distal carbon. It is shown as a circle. The three atoms or groups attached to this carbon are represented by the three lines radiating from the edge of the circle. The next formula is Scalars formula. The Scalars formula is useful for determining whether the two molecules are mirror images or superimposable. To draw Scalars formula, the molecule is viewed in a direction angled to the CC single bond. Then the bonds are replaced with a straight line. These formula are called Scalars formula because these projections are similar to the carpenter's Scalars. Then we will discuss what is dihedral angle. Dihedral angle is the angle formed when one plane intersects another plane. Now consider the planes, a plane containing C1, C2, H, and a plane containing H, C1 and C2 in ethane molecule, right? The angle between these two planes is called dihedral angle. Each conformation has a characteristic dihedral angle. For example, in gauge conformation, the dihedral angle is 60 degree, whereas in anti-conformation, the dihedral angle is 180 degree. Therefore, the dihedral angle defines the molecular conformation. Now, let us discuss the various conformations of alicyclic organic compounds. Dear learners, now let us discuss in detail the conformational isomers of acyclic organic molecules. Let us consider ethane as the first molecule. The rotation about the carbon-carbon single bond in ethane generates infinite number of conformational isomers. Among these isomers, the two important conformers are the staggered form and the eclipsed form. Dear learners, now have a look at this animation. You can see that when the dihedral angle is changing, the conformation of the molecule is also changing, and you can see the two extreme conformational isomers, the staggered form and the eclipsed form. And this is the eclipsed form and this is the staggered form. Among these two conformers, the staggered form is more stable than the eclipsed form. This is due to the fact that in eclipsed form, the distance between the two hydrogen atoms is less than the sum of van der Waals radii. This results in the steric hindrance between the two hydrogen atoms, which makes the eclipsed conformer less stable. And this is the potential energy diagram for the rotation about a carbon-carbon single bond in ethane. And you can see the barrier for the rotation is about 2.9 kilocalories per mole. However, at room temperature, about 84 kilojoules per mole of thermal energy is available to the molecules. Hence, at room temperature, there is free rotation about the carbon-carbon single bond in ethane. In other words, we can say that the conformational isomers, eclipsed form and staggered form and other conformations are in dynamic equilibrium, and these isomers cannot be separated at room temperature. The next higher homologue of acyclic molecule is propane. Let us consider the conformational analysis of this molecule. Like ethane, propane also exists in two important conformational isomers, namely the staggered form and the eclipsed form. Here also, the staggered form is more stable than the eclipsed form. It is due to the distance between the hydrogen atoms at C1 and C3 of the propane molecule, which is less than the sum of van der Waals radii of the two hydrogen atoms. This results in strong steric hindrance between the hydrogen atoms at C1 and C3. And you can see the potential energy diagram for the rotation about carbon-carbon bond. And there is a slight increase in the barrier for carbon-carbon rotation, which is 3.2 kilocalories per mole in propane and 2.9 kilocalories per mole for ethane. Obviously, it is slightly higher than that in ethane, and this high energy barrier for the carbon-carbon rotation in propane is due to the strong steric hindrance between the hydrogen atoms at C1 and C3 atoms. Now let us discuss the conformational analysis of a slightly complex molecule N-butane. In N-butane, the conformational isomers are possible during the rotation about C1-C2 bond or the C2-C3 bond. Now let us discuss the conformational isomers arising due to the rotation about the C1-C2 bond. These conformations are similar to the conformational isomers of ethane and propane. That is, the rotation about C1-C2 bond in N-butane molecule gives the two conformers, namely the staggered form and the eclipsed form. Here also the staggered form is more stable than the eclipsed form, but the only difference between the conformational isomers of ethane, propane and N-butane about the C1-C2 bond is in ethane there are only hydrogen atoms around the Neumann projection formula. In the case of propane, we had methyl group in this position, but in N-butane we had ethyl group instead of methyl in propane. As a consequence, the steric hindrance in N-butane, staggered form of N-butane arising due to the rotation about C1-C2 bond is slightly more stable than the conformation of the propane. And here the rotation about C2-C3 bond in N-butane also results in various conformational isomers. These conformational isomers are different from conformers arising from the C1-C2 bond rotation. Here the C2-C3 bond rotation gives the conformational isomers, namely fully eclipsed form. The first one is fully eclipsed form. In this fully eclipsed form, the two methyl groups are in the same direction. That is, the methyl group at the back carbon is fully eclipsed by the methyl group at the front carbon. Similarly, these two hydrogens, the hydrogen atoms at the backside carbon atom, are fully eclipsed by the hydrogen atoms at the front carbon atom. If you rotate the back carbon atom by 60 degree, the methyl group will move to the clockwise direction and make 60 degree between the two methyl groups, and here the dihedral angle is 60 degree, and therefore the conformer is defined as gauge conformer. If you again rotate this molecule by 60 degree in the clockwise direction, you will get a partially eclipsed conformer. This partially eclipsed conformer is different from the fully eclipsed conformer. The difference is that in fully eclipsed conformer, the methyl group is eclipsed by another methyl group, whereas in partially eclipsed conformer, the hydrogen atom is eclipsed by a methyl group, and the methyl group is eclipsed by a hydrogen atom. Okay. Again, if you rotate this partially eclipsed conformer by 60 degree, we get the anti-form. In this anti-form, the two methyl groups are opposite to each other, and the dihedral angle between these two methyl group is 180 degree, and therefore it is defined as the anti-conformer. The rotation by another 60 degree will give us the partially eclipsed and finally the gauge form. Among these conformational isomers, the antiform is the most stable conformer because it is free from the steric hindrance. There is no steric hindrance between the methyl groups or between the hydrogen atoms. The next more stable isomer of the N-butane is the gauge form. This gauge form is less stable than the antiform by 0.9 kilocalories per mole, and it is due to the presence of steric hindrance between the two methyl groups. You can see that the two methyl groups are in the dihedral angle of 60 degree, and this causes the steric hindrance. Compared to these staggered forms, namely the antiform and the gauge form, the eclipsed forms, namely the partially eclipsed form and the fully eclipsed form, are more energetic, that is less stable. Among these two conformers, namely the partially eclipsed and fully eclipsed, the fully eclipsed form is the least stable or more energetic because the steric hindrance is between the two methyl groups. Hence, we can come to a conclusion that the order of stability of various conformers of N-butane is: the antiform is more stable than the gauge form, which in turn more stable than the partially eclipsed form, and which in turn more stable than the fully eclipsed form. In the next video, we will discuss about the Bayer strain theory and then the conformation of alicyclic and bicyclic organic compounds. Thank you.